Thank you so much, Professor. Thanks for agreeing to do this interview.
My pleasure.
We are at the. I have the sign. Maybe I should put it over there. Maybe if it's interrupted many times, I can do that. Thank you so much, Professor, for agreeing to do this interview. If I'm able to travel in Canada, I do that. I do the interviews in person. I'm glad that this time you traveled to Canada for the GOMD 2025 conference in Vancouver and make some time actually to do this interview. I know that your schedule is tight. Thank you so much.
My pleasure.
Would you tell us more about your academic background? When and where did you go to school, to university?
I graduated from the Slovak University of Technology in Bratislava, Slovakia, Faculty of Chemical and Food Technology back in 1991, so it's a long time ago. And after that, I also did my PhD at the same faculty. But during my PhD, I already took some first foreign training. I spent 3 months at the Brunel University in London. And later on, just after completing my PhD, I spent time at the University of Leeds in the UK. I think altogether it was more than 1.5 years. And then more than 3 years at the Darmstadt University of Technology in Germany under the supervision of Professor Ralf Riedl. So basically, this is my career, and then I assumed a position at the Slovak Academy of Sciences in Bratislava.
Amazing. So this is a typical question I always ask. Why you became interested in glass science?
That's the journey was not really very straightforward. Originally, I didn't think about studying chemistry at all. But when I was thinking about my future career and about my possible employment, I was discussing with my father, and he actually very strongly advised to go for some STEM subjects. Because in the area where I come from, there was a lot of glass, ceramic, and cement industry. I chose silicate chemistry at the end. But originally, I was trained as a ceramist. And also, my PhD was in ceramics.
Yeah.
But when I came to the Slovak Academy of Sciences, I was offered the position in the laboratory of glass. So basically, that was the thing. But originally, I didn't think about scientific career at all. I expected to simply graduate and to find a job in a company.
Yeah. So, but you found the position that you have, and actually the path changed. So, would you tell us more about your research activity during your graduate studies?
Well, during my graduate study, my work was focused already on ceramics. I was working or doing my diploma thesis or master thesis at the Slovak Academy of Sciences under the supervision of Professor Pavel Šajgalik. And it was focused on sintering of silicon nitride ceramics and phase transformation of alpha to beta silicon nitride. So, and that was also, I think that the research was quite successful, and it actually resulted in my first research paper ever.
Amazing. Yeah, that's very interesting. The very first publications, I remember mine a long time back. Now, in your research lab in Funglass, right?
Yeah.
What do you do? What's your main research interest in the lab?
Well, in my position, it's less and less opportunity to do research directly and in person. And Funglass is a relatively large institute. At the moment, including PhD students, we have more than 100 people. So this corresponds also to a very broad range of topics we have, because Funglass has 6 research departments. My primary interest is still related to ceramics, or basically also at the field where glass and ceramics are like interlap, you know.
Yeah.
And my research interest was focused on aluminate glasses, which are rather difficult to prepare because aluminum is not really typical glass former. And then we try to use it in preparation, or use this aluminate glass as a precursor for preparation of ceramics. It's especially yttrium aluminum garnet or materials with eutectic microstructure. But also working in polymer-derived ceramics, where we were preparing with my students coatings, environmental barrier coatings for corrosion protection of metals which are exposed to very harsh environments. But in Funglass, we have many more research topics where I'm somehow involved. We work in biomaterials, especially bioactive glasses, which are doped with therapeutic ions, and also composites, which include biopolymers with embedded bioactive glass, especially nanoparticles. Then we have Department of Glass Analytics, which is focused on development of new analytical methods for analysis of glassy materials, also corrosion and hydrolytic resistance of glass, including bioglasses. We have Department of Functional Materials, which primarily started working on photoluminescent materials, especially from high brightness LEDs, but also for optical thermometry. Now they are moving a little bit away from this, dealing especially with material with photocatalytic properties, both for hydrogen production and wastewater treatment, like photocatalytic degradation of organic pollutants. We have Department of Coatings. There they also interfere a little bit with ceramics because they prepare thermal barrier coatings, also based on high entropy oxides. Then also PVD and PECVD deposited coatings on glass, like functional coatings, which can be reflective or anti-reflective, or self-cleaning or hydrophobic. So lots of activities in this respect. We have Department of Glass Processing, which deals mainly with glass recycling, especially the glass which is not recyclable in standard way, and the special composition, for example, borosilicate pharmaceutical glass, or glass from TV screens, which of course is not recycled, and we are trying to convert them into something useful. For example, again, filters for wastewater remediation or building materials. And at the moment, my research activities in my own department is focused basically on 3 different topics. One are strong glasses. Second are high entropy ceramic oxides, and the third is cold sintering of glass.
Okay, amazing.
So lots of activities.
Yeah. When I was searching your CV and what you have done, it covers a wide range of applications. Bioactive, as you mentioned, bioactive glasses, corrosion, glass ceramics. But another thing is the additive manufacturing, right? In July 2024, I went to another conference which held by American Ceramic Society, ICC 2024, and I learned that the theme of the conference is additive manufacturing. So would you tell us more about this technique?
Well, we do have activities related to additive manufacturing. We have a range of different additive manufacturing techniques, ranging from direct indwriting through fused deposition modeling to stereolithography or binder jetting. And basically, our primary interest in this field is the use of additive manufacturing techniques exactly for the glass recycling, like printing glass into very complex structures, which can be used, for example, for filtration of water. But we also apply additive manufacturing in bioactive materials, printing scaffolds, for example, for bone regeneration, but also the composites based on different types of hydrogels with doped with bioactive glass nanoparticles. So you can make complex structures also for soft tissue engineering, including skin and cartilage.
I remember that I was listening to one of these talks, and the actually presenter was talking about the ability of this technique, additive manufacturing techniques, that a wide range of shapes it's possible to be made using these techniques. I think that's one of the strengths of this technique. And I was thinking that usually the composition dictates the properties, right? For example, in the area that I know in bioactive glasses is the borophosphate or borate glasses, that they are dissolving fast rather than the silicates, so which comes from the composition. But nowadays I see that there are different types of silicate glasses that's offered for wound healing, soft tissue regeneration, that the glass should be dissolved fast thanks to the additive manufacturing, for example, or the sophisticated techniques that's possible to fabricate specific materials that's dissolved fast, like fibers. But in terms of additive manufacturing, it's easy to make scaffold and something like that. So with this big introduction, I wanted to ask, how do you think that these techniques can overcome the compositional restrictions? I mean, composition versus the techniques. I hope that the question was clear.
I don't really think that additive manufacturing can very much help this, because it's very much true that in glass, its properties are very much dictated by composition. What can help in a way is if you prepare glass on a nanoscale, or if you prepare mesoporous glasses, because there you introduce very high specific surface, and then it helps with dissolution, of course. And actually there are some works which suggest that, because there are some like rules of thumb which say that like if the glass should be bioactive, there must be certain proportion of elements, and also the silicate glasses, and they're not quite silicate, and they are usually phosphosilicate or calcium phosphosilicate glasses. But the point is that if you prepare them as nanoparticles or mesoporous nanoparticles, then they exhibit bioactivity, even if they contain quite a lot of silica and not so much calcium and even no phosphorus. This is something you cannot probably solve by additive manufacturing. But what you can do by additive manufacturing is that you embed these nanoparticles in a biopolymer, and by this you can print the scaffold which can dissolve, but the solubility is mainly then dictated by the dissolution of the biopolymer.
Cold sintering, that's one of your area of expertise, I would say. So I was reading about it, and I have a question about the difference between this technique and sol gel. Are they different totally, or?
Oh yeah, that's this is something completely different, because basically sol gel is a technique where you prepare solids in different forms, either fibers, powders, or even bulk materials from inorganic or metal organic precursors. So it's like a chemical way how to prepare solid materials. But with the cold sintering is something different. You already have a powder, some solid, which you want to consolidate. It works in the same way as liquid phase sintering, because in liquid phase sintering you sinter your powder. It contains some sintering additive, which at the sintering temperature, which is usually quite high, creates a melt. And the sintering, the densification and mass transport goes through dissolution, and then the transport of mass is through the melt and then reprecipitation. Actually, Professor Randall, who is here, by the way, at this conference, he came with the idea, I think it was some 10 years ago, that actually, if you know the chemistry, you don't need high temperature. You can replace the melt by a solvent. And then you actually can apply pressure. The temperature, which is to ceramic and glass standards low, is usually the cold sintering temperature shouldn't exceed 350 degrees C. And again, the densification runs through the dissolution, not in the melt, but in the solvent, and reprecipitation. And after that, this transient liquid is removed, it evaporates. And you get the solid chunk of material.
Okay, amazing, interesting. That was a new concept for me. Another new concept for me when I was reading your CV is the paracrystallization. So what does it mean? And I learned that it helps to actually reduce the brittleness of glasses. So how does it work?
Yeah, did I really write paracrystallization in my CV? I don't, because this is not really a topic we have, but principle paracrystalline materials are somewhere on the way between amorphous materials like glass and crystalline materials, like it can be metals or ceramics. And basically, amorphous materials are characterized by the fact that there is no long-range order, or not even medium-range order, that you have only short-range order of the coordination polyhedra in the material. Of course, polycrystalline materials, they have long-range order because the basic cell repeats itself infinitely. And paracrystalline are somewhere in between. That's you have like medium-range order or the domains, which then create the material itself. But quite honestly, we don't really work much in that.
Okay. Yeah, there is an, I actually say that it is part of your research. It was part of the Ph.D. thesis title, something like that. On
we published the topic, but we didn't start it because we didn't find a candidate.
Okay, we will come to this point. We will talk about the Funglass more. Yeah, sustainability in Europe actually is a hot topic. I was reading an article in the American Ceramic Society Bulletin that in the United States, the rate of recycling glasses is quite low in comparison with Europe. So what's the reason for the highest recycling rate in Europe in comparison with?
Well, I think the main reason behind it that Europe really tries to be leader in sustainability and in green technologies. I'm not saying it always works, but Europe is trying to do that. And to be successful, for example, in glass recycling, you need two things. One, you have to create a system, and then you have to educate people so they follow the process. And not in every European countries it is ideal. But as far as I know, in the countries like Scandinavia or Germany or France, where the system is well in place and people are disciplined, I think they are able to collect more than 90% of mainly container glass. And this is important to say, that most of the time when we speak about glass recycling, we are speaking about soda lime silicate container glass mainly. But it doesn't tell anything about other types of glasses, which are very often not recycled at all. For example, pharmaceutical glass is very valuable borosilicate glass. It is not recycled, it's landfilled. So Europe, yes, it's good. And actually the producers are happy, because when they get the glass back, it decreases their energy costs, it decreases their raw material cost, and also it decreases their carbon footprint.
Exactly. Yeah.
So,
it's a greener technique to produce glasses from recycled glass. So let's talk about Funglass. So what's the story of Funglass, when it was born, and please tell more about it. You mentioned about the different departments in it, but
well, when I speak about Funglass and story of Funglass, I call it the journey from the basement. And it's really, it's true. You know, Trenčín is a small town in the west of Slovakia, but it has a relatively long history in glass research. There was a Glass Research and Development Institute founded in 1970. And it has like really good results and very, very interesting projects. But then when the communist regime fell, it was shut down. And it happened to many research institutes because suddenly there were no money to fund them.
Yeah.
But there was one person, his name is Marek Liška. I always have to give him the credit because he refused to accept the fact that the institute where he worked was closed. So he contacted the Slovak Academy of Sciences, got some money from the institution, and bought some equipment from the closed institute for very, very little money, and arranged a research laboratory in the basement of his private house. It's just 3 people. And I came there in 1995. But, you know, it was not working very well. And just after my PhD, that was the last laboratory I was offered to work in. And I was directly appointed to head the laboratory, which was quite difficult situation because I came there and I was the youngest of all, and I was in private house of somebody else, you know, who actually founded the laboratory. I was supposed to be his boss. But in a way, we managed to get some research projects, to start growing a little bit. Then the university was founded in Trenčín in 1997. So we moved to the university and created a joint laboratory between the university and Slovak Academy of Sciences. And we gradually gained more space, more people. Then we got the funding from the European Union. There were structural funds, so we were able. I prepared a project which was called CEXIM, Center for Excellence for Ceramics, Glass and Silicate Materials. We got €4 million to buy equipment, and it was a good start. Back in 2014, the center already had some, I think, 13, 14 employees and 6 PhD students. And then came the opportunity from Horizon 2020 program. European Union realized that, you know, you have these old European countries, and then the new European countries joined later, like 1993-4. Slovakia is one of them. And these countries always underperform in terms of science. So European Union developed tools how to improve their scientific performance. And one of them, the program is called widening, and the specific call is called teaming. And teaming means that you can build or upgrade existing research center with the help of advanced partners from these old European countries. And you get the funding for this for 7 years. And so I contacted my friends. One was Alicia Duran, you know her. The other was Enrico Bernardo from the University of Padova, Professor Boccaccini, Aldo Boccaccini from University Erlangen-Nuremberg, and Lothar Vondracek from the University of Vienna. These are like our 4 key partners. And we submitted the proposal. There were 164 projects submitted in Europe, and at the end, 10 were funded. And we were one of them, the only one in Slovakia. So it was a great success. We got €15 million funding from European Commission, plus €10 million from the Slovak government to build the infrastructure. So that was the start of Funglass.
Yeah, that's a great story. Thanks for sharing. Exactly what you mentioned, starting from scratch, from basement, below scratch. So you annually post the PhD positions. I applied 2019. I was invited to the interview, but I was rejected.
Okay, sorry about that.
That was my story with the Funglass. Anyway, you annually post positions for PhD students. So how you decide who actually decides these positions? How you come up with these ideas? Is there a committee or a person?
Actually, we have a selection committee which consists of the members of Funglass. We also have their representative of students, and also because with the Funglass partners, we signed the agreements about double degree programs. So if there is a student for double degree, we always have a representative from the partner institution in the committee. And basically, we follow the rules which apply all around the European Union. When you want to occupy some position, so you must make a selection procedure which is open, fair, and equal. So we publish the calls. Of course, there are conditions. The candidates must fulfill some requirements about their education, about their background. We define it rather broad because we want a multidisciplinary center. So if you have a master degree in biology, biochemistry, physics, mathematics, material science, materials engineering, chemistry, analytical chemistry, you would qualify.
Yeah.
And if you qualify for that, we invite you for the interview. We cannot exclude someone without the interview.
Yeah? Okay.
So we have to, if you qualify, we have to invite you. Usually, you remember that the interview takes about 20 minutes.
Yeah.
So the candidates have the opportunity to introduce themselves, their master thesis topic, and then the committee members ask. Yeah, it can be, so, and based on this, we make a rank and offer the position to the candidate who ended first. Yeah. And sometimes it happens that the candidate rejects. Yeah, because like he or she can have other position already, or doesn't find the conditions adequate. Yeah. So basically.
Okay. If you are in the selection committee, what are the top 3 most important requirements for you? How do you evaluate an application?
For me, the first, but not the most important, but the first point is that the candidate must be fluent in English. Okay. Because we are very international institute, and our communication language is English. So without English, there is no chance. So this is necessary condition. But not satisfactory condition.
Yeah, of course.
Then, of course, we evaluate the background, whether it fits the topic. It's probably no good if you studied, I don't know, biology, and you apply for a topic in high entropy ceramics. Yeah. It doesn't fit. Yeah. Other thing is that we also evaluate the ability of the candidate to answer the questions and to react, because sometimes the questions are formulated in the way we don't really expect a correct answer, but we need to know or see the way how the candidate thinks, whether he or she can put together various things and to answer. And of course, the last moment is also because we are asking also about the project of the thesis. And it happens very often that we see that the candidate even didn't make effort to read the abstract. So the candidate doesn't know what the topic is about.
Okay. So interesting. So the difference between the PhD positions in the United States again, and I think even in Australia, Canada, and these are in one group, and the Europe in another group, which, as you mentioned, you advertise the position. But in for example, North America, a professor decides to work on a project, and he gets the funding, and then he is looking for a student. There is no committee who decides who should join. At least it's the case in Canada. But as you mentioned, in Europe, there's a committee. So which one do you prefer if you would rather choose between these two?
Yeah, well, first of all, I cannot choose because I'm restricted by the rules. Which
Yeah, of
clearly
course.
say,
Yeah, I mean, if your preference, if you could choose either one.
Well, for me personally, the idea of having committee it seems to me better. But because also advertising the position gives you better selection of candidates.
Yeah.
And quite honestly, in European countries, but I think it's quite similar also in the United States, the interest in studying STEM is not very high.
Okay.
And even if you have master graduates, they usually go to industry because industry can offer much better conditions.
Yeah.
So we actually need to find the candidates elsewhere in other countries. And if we make an open call, then we really have candidates from all around the world. So it has its pros and cons, but I mainly see that it has its advantages.
Okay.
And of course, like you cannot fully evaluate a candidate in 20 minutes, but you get some first impression.
Yeah, exactly. That's the important thing. And also the CV, maybe if they have publication, it helps for the professor, for the selection committee to decide.
But to say one important thing, like, okay, committee is there, but final word in the decision has the supervisor.
Okay.
Yeah, because supervisor is the person who says, okay, I want him or I don't want him.
Yeah. So, GOMD conference. So how did you find it? Did you like this conference? Is there any talk that impressed you?
Well, actually, I was not much at the GOMD. I was mainly at PACRIM.
Oh, yeah, PACRIM. I spent 90% of my time in GOMD, so I forgot about PACRIM.
Yeah, well, of course, there was a great number of interesting talks, like the plenary talk of Professor Harmer was very nice, excellent. Also, the one after that about really the atomic scale examination of grain boundary in ceramics, like amazing work. I saw very nice talks from Professor Bermejo from Montana University at Leoben. He also works a little bit in glass, but mainly in mechanical properties. So a very nice talk about evaluation mechanical properties of ceramics prepared by cold sintering. So a number of very, very interesting topics. The point is, sometimes it's difficult to decide where to go because there are so many parallel sessions here that sometimes you have 5 or 6 talks at the same time which you would like to see, and then it's like really difficult to understand where to go. But overall, like, this is not my first PACRIM. I already attended several of them, and generally it's a very, very high quality conference, very good one with good people and many friends which I can meet.
So you were invited to this conference to give a talk. So what was your topic?
Basically, the topic was focused on an overview of our research activities we do together with some of our partners, the Brno University of Technology in Czech Republic and the University of Sevilla. And it was mainly focused on, the title was the hard-to-sinter oxide ceramics. Can we do it better? Yeah. And I summarized different strategies we applied in the past, trying to decrease the temperature of sintering of this hard-to-sinter ceramics, and to avoid some other things like, for example, elimination of carbon contamination during spark plasma sintering, or using aluminate glasses as precursors for preparation of these hard-to-sinter oxide ceramics.
Okay.
So that was
amazing. The reducing the sintering temperature, it's been always my favorite topic, to see how it's possible to do a magic to reduce the temperature and make glasses or ceramics easier. Let's move to beyond the lab.
okay.
So what do you do at your spare time?
Well, I'm very much outdoor person.
Okay.
So if I have a time, so I spend it in the mountains mostly, hiking, skiing, ski touring, mountain biking.
Amazing.
On average, I probably spend something like 60, 70 days a year in the mountains.
Do you do it professionally, the skiing?
No, I'm just for fun. But of course, I also, with my wife, we have a house with a garden, so it's also a gardening a little bit. And I really like reading books, and both fiction and non-fiction. And if it comes to non-fiction, I really prefer reading about history, which is actually my sort of a hobby.
Okay, amazing. So when you were a kid, what was your dream job?
Oh, well, was nothing with material science, but actually I imagined myself in a way as an explorer. My dream was to be an archaeologist or biologist. But the biologist in the sense like going somewhere to a jungle and looking for butterflies and insects, this kind of thing. But you know, I grew up during the communist time. I was 21 when the regime fell, and during the time it was virtually impossible to travel abroad. So I read books with actually very sad realization. I probably wouldn't be able ever to visit those countries I was reading about. But fortunately, the time has changed, and I really traveled the world a lot.
Okay. In an imaginary world, which job you would like to pick if you could pick another one in a parallel world?
I don't know, mountain guide.
So, do you have any regret in your career, in your life, or anything that you could decide differently after?
No.
Okay.
No. You know, it's there was something I was discussing quite often also with my wife, that whether we would change anything in our lives in the past. But in principle, my conclusion is that like you often do decisions which lead you one way or another.
Yeah.
And you decide one way, and then it's no way how to find out what would happen if you went the other way.
Exactly.
So you must accept that your decision was right.
Yeah. Yeah, exactly.
This gives mind peace, you know.
Yeah. So if a time machine existed, would you travel 100 years back or forward?
Probably back.
You like history, right?
Yeah, not only 100. I would like to see many historical events with my own eyes, from the safe distance, of course. Well, I don't know about the future. I think it's not good if somebody knows his or her future. It's not healthy.
Yeah. Yeah. Also, I would like to go back. I don't like to go forward. So, and for the last question, who is your favorite scientist of the history?
Well, there would be probably several names, but if I come to that, really great person was Richard Feynman, because he was not only great scientist, but also like a very normal person. He was like very humane, and also, as far as I know from his memoirs, he was lots of fun with him. You know, so and perhaps other person is Maria Curie Skłodowska, who actually is really a good example of somebody who, against all odds, could achieve something which is absolutely unimaginable.
Yeah.
Like as a woman at the beginning of 20th century, she managed to be twice the Nobel Prize winner. That's something absolutely amazing.
Yeah, that's impressive. Yeah,
yeah.
That's it. So is there any other thing that you would like to add I didn't ask?
Well, I don't know really. I think it was quite exhaustive list of questions. So.
Thank you for actually making some time for this interview. I'm very excited about it. I mean, I'm happy that we did it in person, and thank you so much. Thank you.
Thank you very much for the opportunity, and
Thanks.